If you've been designing electronics for enough years, you've probably noticed that thermal problems almost never show up where the math says they should. The math ain't mathing, so to speak. You can calculate power dissipation. You can even estimate thermal resistance, and on paper, everything looks fine. But then you button up the enclosure, you run a full load test, and suddenly one part of the system is by far hotter than expected. That's because in real designs, most of the thermal resistance isn't in the heatsink or the enclosure itself. It's in the tiny air gaps and imperfect contact between the parts. So today we are digging into the thermal issues that engineers actually run into. We'll talk about why they happen and how different types of thermal interface materials are used to solve very specific problems. You're listening to Würth Elektronik's What's Up radio podcast, where we're seeing what's up in the world of electronics and PCB design. We'll be checking in with industry experts and Würth Elektronik technical specialists. We're going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and today, thermal materials. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast. So let's start with some fundamentals. Now, in most electronic systems, the interfaces dominate thermal resistance. You can have a beautiful aluminum housing or a massive heatsink, but if the interface between the heat source and that cooling surface is poor, you'll get very little benefit. Air gaps are the main culprit here. Air has a thermal conductivity of about 0.026 watts per meter Kelvin. Even a tiny air gap will completely overwhelm the thermal resistance of the surrounding metal. And in real assemblies, air gaps are unavoidable. PCBs bow. Enclosures don't perfectly lay flat. Component heights may even vary. Even fastener torque variation during assembly changes contact pressure. So this is why simply tightening screws harder often makes things worse. You end up with point contact, uneven pressure, and mechanical stress on solder joints. What you actually need is elastic accommodation at the interface. In other words, a rubber-like material that can absorb tolerances and surface irregularities without forcing rigid contact. Gap-filling materials exist to replace air with something that has orders of magnitude better than thermal conductivity while still conforming to uneven surfaces. The key design variables here are gap size, surface flatness, required contact pressure, and long-term mechanical stability. Elastomeric gap fillers work well for modest gaps where compression is predictable. As gaps get thicker or surfaces become less uniform, the thermal resistance of the interface increases quickly, and the choice of thermal interface material becomes much more critical. Our second problem is assuming thickness versus conductivity is a trade-off. Now, here's where a lot of thermal designs start to go off the rails. These engineers look at thermal conductivity numbers, and they naturally assume that higher is always better. And conductivity does matter, but thickness matters just as much, and very often more. Thermal resistance scales linearly with thickness, so if you double the thickness of a thermal interface, you double its thermal resistance, even if the material itself has a respectable conductivity. That becomes a real issue when you're just trying to fill a larger gap. Now, at that point, even a relatively high conductivity rubber-like gap filler can turn into a bottleneck simply because the heat has to travel through so much material. So you're no longer limited by the heatsink or enclosure, you're limited by the interface itself. This is where intuition often breaks down. The natural reaction here is to look for an even higher conductivity pad, but beyond a certain thickness, you get diminishing returns. You are still pushing heat straight through a thick layer, and that path is dominated by interface resistance. For these larger gaps, how the heat moves becomes just as important as how well the material conducts. Instead of forcing all the heat straight through the thickness of the interface, you allow it to spread laterally before reaching the cooling surface. That reduces the impact of a high-resistance bottleneck at the interface and lowers peak temperatures, even though the physical path the heat takes may actually be longer. Heat doesn't care about distance as much as it cares about resistance. This is why materials with very high in-plane conductivity start to show up in difficult gap-filling scenarios. And we'll see the same principle show up again when we talk about hotspots. So our third problem I want to discuss is when spreading becomes the primary strategy, as well as those hotspots and local power density. Now, in some designs, thickness isn't the main problem at all. Hotspots are another classic thermal failure mode, and they show up even when the interfaces are thin and well controlled. Most boards don't overheat uniformly. One converter, processor, or LED cluster ends up dominating the thermal budget. Everything else looks fine except that one part that's running far hotter than expected. When that happens, adding airflow or a bigger heat sink often doesn't help very much, because the thermal resistance bottleneck is local. You're limited by the area of the heat source, not by the size of the cooling hardware. So in these cases, heat spreading isn't a workaround, it's the main design tool. By conducting heat laterally before it reaches the cooling surface, spreading materials increase the effective area of the heat source. That lowers peak temperatures even if the total power dissipation stays the same. This approach is especially effective when the heat sink or enclosure is much larger than the heat source, if airflow is limited or fixed, or if thickness and weight are constrained. Graphite sheets excel here because they can move heat sideways extremely efficiently while adding very little thickness or mass. Instead of asking the heatsink to pull heat out of a tiny footprint, you give it a much larger area to work with. Our next problem is long-term reliability of interfaces. A thermal solution that works on day one isn't necessarily a solution that works well in the field. Thermal greases provide excellent initial performance because they create very thin bond lines. But under vibration and thermal cycling, grease can pump out of the interface, increasing thermal resistance over time. Mica provides electrical insulation, but it's brittle and it's unforgiving on uneven pressure. Modern designs increasingly favor solid thermal interfaces that won't migrate, they won't crack, and they don't depend on gravity. Phase change materials are interesting here because they behave similar to solids during assembly, but then they soften at operating temperatures. This allows them to wet out surfaces and even reduce contact resistance without flowing away. Thermally conductive insulating pads provide electrical isolation and stable performance under compression, often replacing mica and grease stacks with a single predictable interface. The design goal here is not just thermal performance, but repeatability and reliability over temperature cycling and mechanical stress. Our fifth problem we want to address is combining thermal and mechanical functions because a common and practical constraint is assembly. More and more designs are using small PCBs, LED modules, or daughter boards without mounting holes. Adding screws or brackets increases cost, space, and assembly time. In these cases, engineers need materials that provide both mechanical fixation and thermal conduction. Thermally conductive adhesive tapes solve this by creating a controlled bond line that transfers heat while holding components in place. They are not meant for high-power interfaces, but they're extremely effective for low to moderate power applications where space, simplicity, and repeatability matter. And our sixth and final problem we'll be talking about today is why highest conductivity is the wrong starting point. So by this point, it should be clear there isn't a single best thermal interface material. But this is usually where designs start to drift because the instinctive question is, well, which material has the highest thermal conductivity? And that feels like the right question, but most of the time it isn't. Thermal interfaces rarely fail because the conductivity number is too low. They fail because they're being used to solve the wrong problem. So if you take a step back and you look at how thermal issues actually show up, the deciding factors aren't abstract material properties. They are things like mechanical tolerances, where the heat is concentrated, whether electrical isolation is required, how the assembly is put together, and what the product has to survive once it actually leaves the workbench. So once you start thinking in those terms, a lot of decisions get easier. A thin interface with moderate conductivity often beats a thick one with those impressive numbers. Compression and contact quality matter as much as the material itself, and when geometry or power density limits straight-through conduction, spreading becomes the dominant factor here. The point isn't that thermal interface selection is complicated, it's that it's situational. When you identify where the dominant resistance actually lives in your system, the right class of material usually becomes obvious. And that's why real designs almost never rely on a single thermal interface. You end up combining different approaches, each one doing a specific job, instead of asking one material to do it all. In a real system, you rarely use just one thermal interface material, and a single design might actually use a compliant gap filler for a tall gap, a graphite spreader to reduce hotspots, an insulating pad under a transistor, a thermal tape to secure a small board. And that's not over-engineering, it's matching solutions to the problems. All in all, thermal management isn't about chasing the lowest temperature number. It's about controlling heat flow in a system that has mechanical, electrical, and manufacturing constraints. When you understand where thermal resistance actually comes from, choosing the right solution becomes that much easier. And when thermal interfaces are designed in early instead of added at the end, those systems are getting smaller, quieter, and more reliable. If you're interested in taking the next steps, you can check out Würth Elektronik's Red Expert design tool and calculator to compare different thermal interface materials. You can also compare thermal impedance versus pressure and height versus pressure curves. Visit www.we-online.com/redexpert, and when you're ready to get hands-on, then you can select and order thermal shielding materials or any other component straight from Red Expert. You can also reach out to your regional Würth Elektronik contact, chat with the live chat team at we-online.com/chat, or order directly through the MyWE customer portal. You're listening to Würth Elektronik's What's Up Radio podcast, and we're talking about what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik specialists. We're going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast.